exercise 1006, exponential growth. So any quantity, remember we looked at exponential functions yesterday. So any quantity that increases according to the function, the exponential function y equals b times a to the power of x. Remember we were looking at these types of functions yesterday, and where a is greater than 1. So this is that type of function. If a is greater than 1, your exponential function goes like that, it increases. Okay, whereas if a is less than 1, it goes down. So we're looking at exponential growth in this lesson where a is greater than 1. So this is the equation of this type where a is greater, sorry, not than 0, but a is greater than 1. So the graphs that we'll be looking at look like that. However, often when we draw the graphs, you won't see the graph for these negative values of x here. It'll just start like that. You often won't see these values here, or the negative x values for the graph. As I was saying, these are negative values of x, positive values of x here. Here is x is 0. The graph cuts through at b. Often in these application type questions with exponential growth, you won't see these values. Okay. Now, so the graph grows exponentially, or it increases slowly at first and then more quickly. This is what the curve looks like. An example would be population size of people, animals, bacteria, and investment attracting compound interest. Okay. Because remember, you've got a equals p 1 plus r to the n. So if you look at this investment with compound interest, a equals p 1 plus r to the n. So this 1 plus r is your a bit, which is bigger than 1. You've got your power. P is your b. So a equals p 1 plus r to the n is actually an exponential function. Okay. Flu or computer virus would increase exponentially, size of a bushfire as well. But I think this one, the investment attracting compound interest, would be an example that you may be familiar with, that you've seen the equation for. So you can see that this is definitely an exponential type equation, because it's a number bigger than 1 to the power of n times a constant out the front. Okay, let's look at an example here. So we've got a bushfire is spreading through a forest, and the amount of area burnt is modelled by the exponential function a equals, so I'm just going to write the function here, a equals 5, 1.22 to the power of h. Remember what we were doing yesterday, this is an exponential function. It is of the type y equals b, a to the power of x. Now, remember that the graph cuts through at b. You should be able to tell me that this graph will cut through at, it'll cut the y-axis at 5. Notice when a is greater than 1, the graph looks like that. In this case, your a is 1.22 here. So it's 1.22 to the power of h. So the first question is, what was the initial area burnt? Now let's read what each thing is. So we've got a equals 5 times 1.22 to the power of h, where a is in hectares, so it's the area in hectares. H is the time in hours. When we ask about initial time, that is when time is what? Initially, time is 0. So for part A, you substitute h equals 0, hours equals 0. That is the initial time. Okay? But you could do it that way. The other thing you could do is just know that you will get 5. You will get 5 here, because if you've got a equals 5 times 1.22 to the power of 0, you can either enter that into your calculator, or we know that anything to the power of 0 is 1. So that's 5 times 1. So 1.22 to the power of 0 is 1. And 5 times 1 is 5. However, if you are very familiar with the exponential function and what it looks like, you will know that that value out the front is your initial, is that value of b there when x is 0. Okay? All right, so the initial, so what was the initial burnt area? It's 5 hectares. Okay, now the next question is, what area to the nearest hectare was burnt after 3.5 hours? We know what to do here. What do you substitute? Anyone? After 3.5 hours. Yeah, substitute h equals 3.5 hours into your equation. So a equals 5 times 1.22 to the power of h, which in this case is 3.5. So to the nearest hectare, that's 10 hectares, or HA. Okay, so 10.028 to the nearest hectare, that's 10 hectares. Question C, after how many hours will 20 hectares of land be burnt? Question C, after how many hours will 20 hectares of land be burnt? So we're subbing A equals 20 into the equation. So our equation is A equals 5 times 1.22 to the power of h. So we've got 20 equals 5 times 1.22 to the power of h. What is my next step here to solve this?
Guess and check.
Well, it's actually what we can do. Look, guess and check used to be in the course. They say that it has been taken out from 2014. So look, if we know that when h is 3.5, you get 10 hectares, it's obviously going to be more than 3.5 hours. What we could do, we could just, here, if you want to work out what that is, yes, you could guess and check, but, you know, here you could divide by 5. So 20 over 5 equals 1.22 to the power of h. So, because this is 5 times that. So 4 equals 1.22 to the power of h. Now, you obviously can't, the only way to do this would be guess and check, but guess and check is out. But we're going to just practice it anyway. So it's obviously going to be bigger than 3.5. You could try, say, 4 or 5. You might try 5. All right, so try h is 5. I wouldn't try h is 3. What's 1.22 to the power of 5? 1.22 to the power of 5, anyone? No, we need to get 4. 1.22 to the power of 8.
Yeah, it's 4.9.
All right, try 1. So if h is 8, you get 4.9. That's too high. Let's try h is 7.
4.0.
Yeah, so it's 4.0. So, and then you could go back to the original equation and go 5 times 1.22 to the power of 7, and you'll get 4.0. So you'll get 20 in that case. So what I've done, I divided by 5 to get the 4. I now need the value of h that gives me 4, or if you don't like doing it that way, you could stop here and just try different values of h to get 20. And the smallest value of h, that will give me 20 if I put it in here, or that will give me 4 if I put it here, is 7. So it would be 7 hours. Now, that is out of the syllabus, guess and check. All right, that used to be in, but it was quite time consuming. Whereas they may ask you a similar question instead on the graph, okay? So.
So it was double.
Yeah, but no. How many hours would 20 hectares burn out? After 7 hours. Now we have to graph the function. We have to graph the function of, for values of h from 0 to 6. We've already got some values, so we've got 0, no, 1, 2, 3, 4, 5, 6. I don't think we can, going to have to just put them 2. We can't do doubles, like 6. And look, we already know, we need to look at some areas. We know that 20 hectares after 7 hours, which would be here. So we only need to graph up to 6. So let's just make this area thing go to a maximum of 20. Okay, so what are we going to go up by? 2, 4, 6, 8, 10. You can go up by 2s. Okay, so we've got 2, 4, 6, 8. Be careful with these. 10, 12, 14, 16, 18, 20. That is your area in hectares. And that's your time in hours along the bottom. Now be careful, if I'm going up by 2s, it means that 5 small squares equals 2. What's 1 small square? You go 2 divided by 5, right? I have a difference of 0 to 2 there, and that occupies 5 squares. So you go 2 divided by 5 is 0.4. In other words, the scale goes up by 0.4. You need to if that's 0 and that's 2 and there's 5 jumps to get there, you do from there to there is 2. 2 divided by 5 jumps. Each little square is 0.4 unless we put something else on our axis. Little error there, that's a 20. Okay, so scale goes up by 0.4. Let's graph. So when h is 0, we already saw initially when h was 0 that our area was 5. Now, I wouldn't be worried here about jumping up by 0.4 because 4 is exactly halfway between, 5 is exactly halfway between 4 and 6. If there's 5 spaces, you go at 2.5. That's 5. Do you get it? It's halfway. 5 is exactly halfway between 4 and 6. You could go 0.4, 0.8, and another 0.2 in the middle would give you 5. I'd probably put that on my graph. Now, when h is 1, we need to do some substitutions. We know when h is 3.5, so I'm going to do the 3.5 point. 3.5 is 10. Now, we need to do some substitutions on our calculator. So, when h is 1, 2, so I'm just going to maybe do it over somewhere or up here. All right, when h is 1, area is 5 times 1.22 to the power of 1. Anyone? You need to work some of these out. So when h is, so we get 6.1. So 1, 6, that's 6.4. Look, you want to just go slightly above the 6. What about when h is 2?
7.4.
1 decimal place is fine. 7.4. 2 is 7.4. Now I've got 6, 6.4, 6.8, 7.2. 7.4 is exactly going to be halfway between 7.2 and 7.6. So that's where you've got to have your accuracy there. It's not really looking exponential yet. I don't think you need to do h is 3 there. Maybe h is 5 would be a good one to do. Let's do h is 5. Someone already worked that out before, but h is 5 is 30. So when you do h is 5, we get areas 13.5. 5, and if this is 12, 12.4, 12.8, 13.2, 13.6, just under that. So just under that. And let's just do when h is 6, what do we get? It's obviously less than 20.
16.4.
So for h is 6, you get area is 16.4. Sorry, you can... now, we've got 16. 16.4 is 1 box up. And that's it. So we're going to join those lines. I really don't need to do h is 3 there. Remember, the curve is like that. It's a curve. It's not a straight line. Okay, so a smooth curve through the points. All right, it must be a curve. I might just put 7 in there. We know 7 was 20 from our question in the other part. Okay, so notice that is an exponential curve. You can't see the other bit down here, but often with the application type questions, you will not see it because they often start at time is 0. Okay? Okay, now you just have to use your graph to determine after how many hours 10 hectares will be burnt. So we can come across 10 hectares and come down. Actually, we had that in one of our questions. Anyone? That was in question B.
Oh, yeah.
It's
Oh, is that like a half?
yeah, but after how many hours will 10 hectares be burnt? Coming across at 10 hectares, coming down, that's actually 3.5 hours. But that question was in part B. Anyway. What is the area burnt after 5.5 hours? If that's 5 and that's 6, 5.5 is exactly halfway between, which is not on a line, but in between these two lines there. And that looks like it's hitting exactly here. Now, be careful there. Remember, my graph is just approximate. Now, look, it is sitting about 14.8, but I would just say that it's approximately 15. That is approximately, Because it just depends on how my curve is drawn. I've got about 14.8 hours, but I go just approximately 15 hectares. All right, that's close enough. All right. Yeah, everyone's curve will be slightly different. Mine's actually sitting at about 14.8 hectares, but it just depends. I'm reading off 14.8, which is approximately 15 hectares. All right. And what are the limitations of this exponential model? It's going up and up and up. All right. So the model assumes that the area burnt will just continue growing quickly. Because see, it's sort of growing slowly here, but then as we get up here, this is just going to take off and almost be vertical at some stage. All right, that's how an exponential curve goes. With more time, it increases much more rapidly. Okay, so, but that's not what often happens in a fire if there's a change in weather, change in wind direction, whatever. So the model just assumes that it just keeps burning at that exponential rate and doesn't take other factors into account. Growth or functions, past HSC questions. So the mass M of a baby pig at age X days is given by M equals A times 1.1 to the power of X. So it's exponential growth. What's inside here to the power of X is greater than 1. A is going to be your initial amount, all right? So it is of the form, as we said, this M equals A times 1.1 to the power of X is of this form, Y equals B times A to the power of X. That's what we were looking at yesterday. We can see the A is the B, and this little a here is the 1.1. All right. Now it says, what is the value of A? Now, the mass M of a baby pig at age X days is given by this function where A is a constant. The graph is shown. Now looking at the graph, remember what we said when we saw the graphs Y equals B times A to the power of X, and we sketched them, and what value was this here? That was B. Well, let's look at the graph. Can you see what the value of the B, what we think is B, is? Sorry, from the graph. What is it? Yeah, so B is 1.5. So girls, there is no other way that you can work that out without looking at the graph. That's the only place you can find it. All right, so the value of A, so from the graph, A equals 1.5. The other thing you could do is, to show some working out, is from the graph, when D, when the number of days, when X equals 0, the mass is 1.5. That's what we can read from the graph. So from the graph, so for those that know the form of the exponential function and know that it cuts through at B, you'll be able to say that A is 1.5. If you forget that, what you can read from the graph is that when X is 0, M is 1.5, and substitute into M equals A 1.1 to the power of X. That's the other way we can do it, if you want to do it by substitution. So you get 1.5 equals A times 1.1 to the power of 0. We know that 1.1 to the power of 0 is 1. And here we can see that A is 1.5. So that's two ways of doing it. It's only worth 1 mark. They're hoping that you'll be able to recognize that that is that value of B that we've been talking about, and that it equals the very beginning point when X is 0 on your graph. So part 2, what is the daily growth rate of the pig's mass? Write your answer as a percentage. You know how we said this type of graph, an example of this type of function is compound interest? That's what's going to help you if you have that, so like remember that sort of application. If this was like a compound interest formula, right, this pretty much is the compound interest formula, all right? Where did this 1.1 come from? I'm going to write what the compound interest formula is. All right, you tell me what the R is, the rate of growth. It's 0.1. Okay, now, as we said before, compound interest is an application of exponential growth. So when you see something written like this, A times 1.1 to the power of X, this 1.1 is 1 plus R, 1 plus this rate. All right, and that x is to the power of n. So from this and comparing, the daily growth rate is 0.1. Now that is as a decimal, which equals, timesing it by 100. You know how when we use the compound interest formula, you always write your r as a decimal. It's 0.1 times 100%, because normally we write whatever our rate is, put it over 100, which is a 10% growth rate. So that's the daily growth rate. Now, what we could do is see if we can sort of work it out from the graph. It might be a little bit hard, or we can substitute some values in to try and work it out from the graph. So that's one way to do part 2. I'm going to try another way of doing part 2. So let's say I look at a point on the graph. That might help me. That after 3 days, the mass is 2. Can we see that? I'm looking at a point on the graph and hoping that it'll help me. After 3 days, the mass is 2. So I know my formula is m equals a 1.1 to the power of x. I'm going to substitute m is 2, x is 3. I'm going to try and do part 2 another way. One way is to recognize it as a compound interest type application. The other way is to substitute a point. We also know that a is 1.5 from part 1. Okay, so I've got 2 equals 1.5. This is just not going to help me, is it? You just got to recognize it as that. Okay, it's not going to help because I've got everything there. Do you know what I mean? There's your rate. No, don't do it like that. But if this had 1 plus x, maybe you could work it out. All right? But it's in the formula. You've just got to recognize the formula. No point substituting. All right? If I had 1 plus r here, I could work it out. But I've already got that it's 1.1, which is 1 plus r, which is 1 plus 0.1. So the rate is 0.1. I'm not going to get you to do all that work for 1 mark either. So that is not required. It's here. That's how we're doing it. All right? All right, now, this question continues from some other question, which we don't really need it, where we don't need it. So this is from the specimen paper, question 29. It continues from part 1, where the capacity of the water tank is found to be 2862 litres. Now, so we've got a water tank with 2,862 litres. The tank was found to be leaking, losing 5% of its volume each day. So this is not an exponential increasing curve, it's a decreasing curve. You know, if it's losing 5% each day, you know how compound interest is a equals p 1 plus r to the n? If, yes, it's minus depreciation 1 minus r to the n. I'm just going to show you where this is the formula, v equals b times 0.95 to the n. We were looking at this type yesterday. This type of curve goes down, not up. The reason is because you are losing, because your rate, you're losing 5%. So you're not going to have like 1.05 here. It's coming from this. 1 minus 0.05 gives you 0.95. That's where the 0.95 is coming from. It's coming from 1 minus, now 5% as a decimal is 0.05. That's where the formula is coming from. That's like a depreciation formula. Okay? So, this type of curve doesn't go, it's not exponential growth, it's what we call exponential decay. Goes down. Okay, so this is the formula. V equals B times 0.95 to the power of N. Now, V is the volume of water remaining in the tank. B is the volume of the tank when it began leaking. So it's the initial volume. And N is the number of days since the tank began leaking. Now, it says the tank was initially full. How much water had the tank lost 3 weeks after it began leaking? So you've got to get your units correct. It loses 5% of its volume each day. So when we're going to be dealing with time, it's got to be in days. All right? So N is the number of days. So what do you think I know? The tank was initially full. Do we know the original volume? Come on. When N is 0, so at the very beginning of time, when N is 0, what was the volume in the tank? Anyone?
2
2862 litres. Very good. So we can substitute it in, but can anyone tell me what that B is without me doing any substitutions? B is always, yeah, it's your initial. It will be 2862, but we'll do it by substituting. So we know that when n is 0, after no days, initially, the volume is 2862. We can substitute it into the equation that they gave us. So I've got 2862 equals B times 0.95 to the power of 0, because n is 0. Anything to the power of 0 is 1. So we can see that B is 2862. Now this value of B out the front is always your initial conditions, your volume initially. So we know that. So now we can update our formula to be V equals 2862 times 0.95 to the power of n. Now the next question says, how much water had the tank lost 3 weeks after it began leaking? Assume no water was added during these 3 weeks. What do I substitute now? Anyone? Substitute n is, well, it's 3 weeks, but we don't put, yeah, n is 21 days because it's 3 weeks. So really, those are the sorts of mistakes people might make. They won't read the question properly and they'll substitute n is 3 instead of n is 21. You must, it's really important that you highlight or something, n is the number of days. And this is 3 weeks. You want to be highlighting the important information. All right? So I've got V equals 2862 times 0.95 to the power of 21. Now, and then when you've done this, you need to go back and read the question very carefully as well to make sure that you're actually answering it. Does anyone have an answer after this substitution? 974.66. All right, litres. Now, let's go back and read the question. Have we answered it? How much water had the tank lost? V is the volume of water remaining in the tank. I need to do something else. You have to subtract. So the volume of water lost. So is 2862 minus 974.687, which is, anyone? 1887 point. I'll just go, yeah, to 1 decimal place. 3 litres. 1887.3 litres, giving it to 1 decimal place. So please, how much water had it lost? The formula doesn't give you how much it lost. The formula just gives you the volume of water remaining in the tank. So you know initially there was 2862 litres. Now there's only 974.7 roughly litres. It's lost. You have to, what it's lost, you have to subtract to work it out. Okay? So we're going to turn over and look at the 2012 HSC question 30. Okay, look, we've got 2 exponential equations. Because this one goes up quicker than this one, we would expect that the rate of which one would be higher than the other. The dotted line, which one has a higher rate of increase? The higher one. So you know how we know this is an application of A equals P 1 plus R to the N? The R for this graph here would be greater than the R for this one here, whatever it might be. This B might be a whole number too, so I'm not quite sure. Well, we'll see. Okay. So in 2010, the city of Pythagoras built the predicted population of the city using the equation A equals 1.04 to the power of n. So when you see that equation, sorry, P equals A 1.04 to the power of n, you should be able to tell me some things. What was the rate of growth of this population? This is 1 plus R. What's the R here? 0.04, which is what as a percentage? 4% growth. Okay, so this is predicted population 1.04 to the power of n. That year, the city introduced a policy to slow its population growth. So this is actually what's happened here. All right, so this was the model of what they were expecting. And then they introduced a policy to slow down the population growth. The new predicted population was modeled using the equation P equals A times B to the power of N. Now this B may be a whole number. It's not, it may be a whole number, may not. More than likely not going to be a whole number, okay? In both equations, P is the predicted population and N is the number of years after 2010. Now the graph shows the two predicted populations. And the question says to use the graph to find the predicted population of Pythagoras in 2030 if the population policy had not been introduced. So we're looking at which graph? The dotted one or the other one? Dotted, 2030. And we come up and we go there. I think it's sitting on this. Look, to me it looks about halfway. What do you think? Or tell me what it's going up by. What does that scale go up by? We've got 6 million, 7 million, 5 spaces. So it's 1 million divided by 5 spaces. It's 200,000 each box. 1 million divided by 5 spaces is 200,000. That's what each box goes up by. So the only thing here is, I think it's sitting exactly, do you think it's sitting on the line?
Yeah.
I think it is.
It's 6,600,000.
So it's 6,600,000 or 6.6 million. So for part 1, use the graph to predict the predicted population. In 2030, it's 6,600,000 or 6.6 million. Please make sure you put, you know, you've got to read the, you're lucky that that doesn't just say 6 and in brackets million, because people might put 6.6 without units, but 6,600,000 is fine. Or you could write 6.6 million. All right, question 2 says, in each of the two equations given, the value of A is 3 million, right? We can see that. What does the A represent? The what? Initial? The population initially. Well, actually, you tell me from the graph. Isn't it the population in which year? So the 3 million equals the population in 2010. Do you see that? Which is initially from when they started this model. Okay. Now it says, ready? It says now from 2014, solving nonlinear equations using a guess and check approach is deleted from the General 2 Maths course, and then they're asking you to do guess and check here. Okay. So it says explain with or without calculations why 1.05 is not a suitable first estimate for B. You know how we said this first graph up here has a higher rate? This you might estimate not 1.05, it should be something like 1.02, 1.03. Do you understand? It's got to be smaller than 1.04. This has a higher rate. So if you look at, so part 3, part 1, you've got P equals A, 1 plus 0.4 to the power of N. Really is P equals A, 1 plus 0.04 to the power of N. So if the graph is not as steep or is flatter, R will be smaller. You know, remember we're modeling this on P equals A, 1 plus R to the N. So R will be smaller. You would expect, we expect R to be less than 0.04. Do you get it? So, in other words, the bit in the brackets should be less than 1.04. Does this make sense? Remember we were looking at curves yesterday, and as the value of the B, the number in the bracket got bigger, the A, the curve got steeper. Okay, so an example might be, you know, you might have something like this, 1.03 to the N, or P equals A 1.02 to the n. You would expect something like that, not bigger than 1.04, all right? Okay, now, so it says with or without calculations why it's not suitable. That is without calculations. You could try 1.05 to the, I don't know, to the power of 10 and show that you get a bigger number, all right? But that's without calculations. And then it says, they do give you, this is not going to be in there anymore, but, so with n is 20 and the population is 4.46 million, they want you to use the guess and check method and that equation A equals B to the power of n to estimate the value of B to 2 decimal places. Now this would be quite, we already know that it's going to be either 1.03, 1.02 or 1.01. It's got to be one of those, all right? But you don't have to do it anymore. They do say show at least 2 estimate values for B. But just by our reasoning and knowing what the graph should look like, we should know it should be one of those. Look, if we were to try one, I wouldn't try 1.03 first. I'd try 1.02 because it's if it's too low, you can always try the 1.03, all right? So I'm just going to do an example using n is 20, but we don't. Remember, it is out of the course. I'm going to try that 1.02, okay? So I've got a P equals A 1.02. That's what I'm going to try. I'm trying to get a population of 4.46 million. We know that the A is 3 million, but like I said, this is out of the course now. 1.02 to the power of 20. Anyone have a go with 1.02? Yeah. Don't put in the 4.46 million thing. Just put 3 million.
4,457,800.
And look, that's probably going to be the answer. Because if you try 1.03, it's going to be too high. So that's very close. And look, this 4.460, if you round this off to 3 significant figures, you get that. And they only want it to 2 decimal places. So if you did try 1.03, you'd get a much higher value. You would get 3 million times 1.03 to the power of 20, and I'm sure that that's going to be really high. Okay? Anyone try 1.03? But like I said, it's out of the course now. Okay, that'll do. So this is way off the 4.46 million. So that's too high. So this 1.02. So 1.02 was a good, that's a good estimate for B. But we don't have to do that anymore. You can see that it can be quite time consuming, all right? Now, in the last part of the question, it says the city of Pythagoras was aiming to have a population under 7 million. In 2050, does the model indicate that the city will achieve this aim? Justify your answer with suitable calculations. So now that we know that B is 1.02, right? So we now know that our new formula is P equals A times 1.02 to the power of n. We've worked that out from part 3. And it says that they're aiming to have a population of just under 7 million in 2050. Now, in 2050, I have to see what value of n, so that says in. In 2050, I need to see what value of n I substitute. So I need to go up to the graph. Okay, 2050. What am I going to substitute? If 2010 is year 0, 2020 is year 10, 10 years, 20 years is 2030, 30 years is 2040, what would 2050 be? N is what? N is? It'd be the next one up. N is 40. No, because 0 time is 2010. 10 years is 2020. 20 years after 2010 is 2030. Remember, 0 time is in 2010. 2010 plus 40 gives 2050. So for this question here, in 2010, you substitute n is 40. Okay, so we use our formula. P equals, we know that 3 million is the value of A, 1.02 to the power of 40. And it's saying that they're aiming to have a population under 7 million. So when we do this substitution, we need to see if our answer is going to be below 7 million. Has anyone worked that out yet? Achieve what it wants to. We're aiming to have a population under 7 million in 2050. Does the model indicate that the city will achieve this aim? What do you think? Which is? This is less than 7 million.
So yes.
So the answer is yes. The model achieves its aim. Okay?
Somebody's with the star 500.